Welcome back on Electronics 2, and today we are going to have a look on our common emitter. Welcome back to Electronics 2. Today we are going to continue with our lesson, and our lesson today is going to be based on the common collector. And with a common collector we have some specification. We're going to have a Darlington pair, we're going to have a cis-clear pair. Sorry, it's really difficult to spell, but you can see. So it's just some specific application of our common collector amplifier. And then without taking time, as we say, we have three configuration of an amplifier. And the first one, we have the tree, which is a common emitter. We discussed it in our previous lesson, and then we did some problem solving, we did some example, we understand and we master what is it about. So today we are going to have a look on our common collector, which is on point 3. I think it's a mistake, but we gonna have a look on this one, common collector. The common base, it's simple. We gonna have a look on it lately, so that we can carry on and have a look as well on our common on some theory, which is chapter 8. Okay, so without going further, you can see that it's all about the common collector amplifier. So this is our configuration. Okay, so what do we need to keep in mind about it is that usually it refers as a emitter floor. Okay, and then the input signal is applied to the base through the coupling capacitor of the output voltage. Okay, so one thing we are going to observe is that with this common emitter, we're gonna have a output which is gonna be from here. Can you see from the emitter? The output is from emitter, but input is on the base. Can you see? So that's basically what we need to write down about it. And then we're gonna have a look as well. We're gonna say that the voltage gain of a common collector amplifier is almost close to 1. And its main advantage is high input resistor and current gain. Okay, and therefore there is no phase inversion. So it's one of the note that we are going to note as well. The output is approximately the same amplitude as the input. So it's also one of the note that we are going to write down. Okay, but when we have a look on our R emitter, which is basically a parallel between RE and R loop. Okay, so one thing we are going to observe in this circuit is that when you're doing the AC analysis, you'll find out that your R load is in parallel with your R emitter. So this is our R emitter. Okay, and therefore because of that, without the load, this is going to be our R in base. Okay, but if we have a load, this will be our R in base. What change? Just that this is a parallel between what? The two, the load and the R emitter. So that's basically what happened with this question. Okay, so let's move on some basic as well. We can see that basically that is straightforward. So we said the voltage gain. Okay, knowing the voltage gain is the ratio between the output. Okay, I think the output here, it's our VE, and then the input is our V base in this case of the collector. Okay, so as you can see, it's going to be V out over V in, VE over V base, and therefore our V out is going to be this given by this equation, Ohm's law, but V in is going to be the addition of the two resistors, which going to give us the output, and therefore the voltage gain will be calculated by that. Okay, and then on the next point, we're going to see that where is no load, R is equal to R emitter, then the average is equal to 1. So if we don't have any load, the average voltage is going to be equal to 1. But if we the input resistor, that's how we calculate our R input. We know already the average current gain is given by that, and then the input is given by that. So basically it's just a repetition, so we don't have much, but you're gonna understand them very well when you're gonna be doing our calculation. And then I talk about the Darlington pair, which is this configuration. Okay, so as you can see, you have a configuration like this. You're gonna have a beta AC2, then here you have what? Beta AC1. So it's like you have two beta DC, so the two, they are going to combine each other. So this is going to increase our internal resistance, okay, our R input. So we are going to improve that internal resistor, okay. But you're gonna have a look on it when we are doing example. If you want to go deep into it to do some example and understand it properly, you can read your textbook, and then that's it. So which means when you're calculating your R in base, here, it's going to be given by the combination of the two, beta AC1 and beta AC2. You're going to have a look on it in the example video, problem solving video. And then we have this as well, which is another application, and the configuration, it's something like this. You can have a look on it into the textbook, but they don't really ask question about it. So that's it about our common collector. But when we start solving problem, you want to see how to approach it, and it's really simple and straightforward.